So please join me in welcoming Professor Jordan for what's guaranteed to be a very inspiring CSA IISc distinguished. With that.
All right, thank you. It's a great pleasure to be here. Thank you for that very nice introduction. And thank you, Chiru, for hosting me. I saw him just 2 weeks ago. We had a reunion of my group in the south of France. And Chiru came to that reunion, and there was about 120 people there. So it was postdocs and students from all years, and a real opportunity to see a great community of people. Many leaders in machine learning were there. So it is a pleasure to be here. I'm glad that this is not a huge, overwhelming crowd. Sometimes with machine learning, you have thousands, and it's just like being on the stage. It's not interesting. This is much better. It's more like I'm used to. So, so since it's a relatively intimate crowd, so please just ask questions as I go. Just have it maybe be for a little dialogue. I'm also certainly happy to have questions at the end, but also that way would be nice. So yeah, I'm going to give a talk that is not just one thing. It's a number of different projects that are all recent projects, but they reflect a longer term vision. In this case, having to do with machine learning and macroeconomics. Okay, so let's just start talking a little bit about machine learning, and then of course AI, which is the terminology that people are now using for machine learning. So machine learning itself is really a blend of statistics and computer science. It's algorithms doing statistical predictions and inferences. Okay. Now there are two sides to that endeavor, at least, probably more. But one of them is to make good predictions, and that's what neural nets do in deep learning and all. They're very good at making predictions. In fact, the large language models that have been so much discussed are really just algorithms that predict the next word in a sentence. Do it in a sophisticated way, but that's all they're doing, are prediction systems. So prediction systems are now a commodity. You can download software that does it. It's widely used, and there's now a lot of business models based on that. So that's all to the good. The problem, though, is that when you put these systems in real life, interacting with the real world and with us, lots of problems arise. And they're not just easy problems to fix. They have to do with the systems perspective that's missing. If you just think about prediction. In particular, let's talk a little bit about decision making, which is the other side of machine learning, and think about that a little bit. All right, so first, to kind of get into this topic, I think it's useful to not just think like an academic. It's always useful to think what's in the real world, what's happening in the real world, what are the trends and what's going on there. And so I would argue that machine learning is really an engineering field that arose in the real world more than in academics. It's really analysis of data and making predictions at very, very large scale. So the large scale is kind of new, and that really happened in industry. So already, 20 years ago, you had systems in the back end of very large companies. So think about Alibaba in China, think about Amazon in the United States. These companies were taking in vast amounts of data, and they needed to do things of making predictions, like the supply chain. What's the probability that a certain shipment is going to get through at a certain time, so that I could make promises to my vendors? And those supply chains were already very, very large scale, and now there are 1 billion products being served to hundreds of millions of people. So there's nothing like it in history ever before. No supply chain ever this big. And so there's no hope that kind of classical methods or individual humans could sit down and run that supply chain. So that already 20 years ago, it was necessary to build algorithms that made the predictions about supply chain. So at Amazon, they did that with a technology called random forests. And it's just about as good as deep learning. It's somewhat similar. You could take one out and put the other in. You might not notice the difference. They built a whole infrastructure to run random forests. And that infrastructure included tens of thousands of computers. And it was the beginning of the cloud. This is where the cloud came from, was to run random forests for predicting supply chain at Amazon. Okay. All right, so that was sort of a lot of development and very important, obviously, to the economy, and it's continuing to go on. I think the second phase was when companies like Amazon realized a lot of their data was about humans and human choices and transactions, and not just about the real, the supply chain. So they'd say, okay, you made certain purchases, I'm going to recognize you, and I'm going to give you recommendations for other purchases you could make. That's a recommendation system. Again, it's based on very large-scale data analysis. When the scale gets large, it works better. Nice. And it had a huge impact on the economy. Recommendation systems are used all over the place, and you don't even know that you're using them, but they're being used all over the place. Okay, so that's really important. Machine learning really developed out in the real world. And the algorithms were relatively sophisticated. I think the third phase is the one we're in now, where there's so much hype and so much discussion. And it's the same algorithms. It's gradient descent on large data with, the cloud. The algorithms haven't really changed that much. But now the data is not just about human data. It's actually human data coming from humans like speech and natural language. So the outputs of these systems that make these really good predictions look more like humans. They can write. They can make speeches. So people looked at that and they said, wow, that's amazingly good. This must be AI. Finally, AI has arrived. Of course, it was just machine learning, nothing new, but it was called AI. And of course, that has led to a storm now of discussion, most of which is just kind of crazy. But it is real. It is machine learning algorithms that do real things. And so you can build businesses on it, and it's going to change the economy. But it's not the old AI. Right? But in the meantime, I think there's something more interesting emerging, which is that these systems are not used mainly to just make, like a human being, a sequence of decisions, or to replace a human being. They're used to build new kinds of markets. They're bringing producers and consumers together in new ways. Think about medical systems that bring doctors and patients together in new ways and bring data together with both of them. Think about transportation systems and commerce and so on. These are real-world systems that are used machine learning, but it's not just a prediction problem. It's a market-building problem. And that needs to be thought about that way by the technology people like ourselves. Okay, so let's return a little bit to this issue of what is it, if we're going to call this AI, what is it, right? And so here's another perspective, which is that every 50 years or so, a new engineering field emerges, okay? And usually there's an underlying scientific development that precedes the engineering field. So for chemical engineering, it arose in the 40s and 50s with polymers and other chemicals. And before that, there was an understanding of basic chemistry. There was quantum chemistry and fluid mechanics. So you knew what happened when molecules came together and made new molecules. But it wasn't at all clear you could build that in a factory, in a field. In fact, people would try. India was actually pretty well known for trying to build factories to do chemistry at scale. And some of them would work, surprisingly. Some of them would explode and hurt people. And some of them just didn't work at all. And so new mathematics were needed and new ideas were needed to make this viable at scale, chemistry at scale. And that became called chemical engineering. It has its own principles. It's new. Same thing with electrical engineering. Before there was electrical engineering, there was Maxwell's equations. So there was a full understanding of the phenomena. Right? But the idea of how do you bring electricity into a city and into a home and not burn down the home? How do you build circuits? How do you do communication over the electromagnetic waves? All that was new and needed to be developed to build an engineering field on top of Maxwell. All right, so I think that's what's happening now. We have principles of statistical inference, making decisions under uncertainty that are rigorous. And we have principles of algorithms about how to scale certain processes. So we think we know how to put those together and do it at scale for hundreds of millions of humans. Right, but we don't really. Sometimes we put it out there, we make a social network, and it sort of works. It does something interesting, but it also hurts a lot of people. And we don't think about what is this doing? What was the goal? What's working and what's not? What's success? What's not? All right, so I believe that that's what happened. Is a new field is emerging, and I think these old style AI style thinking is hurting the emergence of this field. Okay, so what does that mean? Well, the AI perspective, this is the 1950s, it's John McCarthy, it's what you learn at the university, was that we need to think about how to put thought in a computer. We need to understand intelligence. If we understand that, then great things will happen. Okay? Now, it's kind of a little strange because intelligence is not, what that is. But in the 50s, it was quite reasonable. We didn't have computers before that, so computers seemed to be they had hardware, they had software like the mind and the brain. It seemed to be something like, intelligence could emerge. That's interesting to think about and try to work on. So they did. It didn't deliver. It didn't yield algorithms that do thinking in a computer. Okay? It failed. It'll eventually, we'll have thinking in a computer. But it didn't work. And what worked was machine learning. Okay? So different. And machine learning arose, like I said, through things like supply chain, things like search engines, lots of machine learning there, advertising, markets, and so on. All right. So, so the goal was to have intelligence, and it's not clear what intelligence really is. Is it human intelligence, or could it be swarms of animals? Could it be markets? Are all those things intelligent or not? It wasn't clear. Still isn't very clear. So, but one of the goals would be, the Turing test said, well, to be intelligent, you have to be able to respond like a human, and you have to be autonomous. Because if you're not autonomous, you're tethered to a human. Obviously, the human's giving you the intelligence. So it became about intelligence that was autonomous. And I think that's a real mistake. All right, so not a lot of thought went into this research agenda. And I would argue this is just wrong. So the right way to think about intelligent systems is about the collective, not about a single smart computer. It's about the collective in which it's embedded. And the collective will be humans, but also other computers and also devices of all kinds. That's the collective. And you got to say, what's that system doing? And what do we want it to do? Right? If you don't talk about that, you're not being a good engineer. All right. So if this is an emerging engineering field, it is. But what are the principles? Well, you have to talk about them at the level of the collective. And so this idea of mimicking human individuals is just very point-wise. It's not thinking about the system. All right. Secondly, this idea of autonomy is really more about show off. I got a robot. Look at the robot; it can do things. It's a show off. I've created this thing, like Frankenstein mythology. And I see the other day there was like in South Korea an orchestra that was being directed by a robot. It's a show off. It's not real. Right? And I think it's dangerous because it creates all kinds of wrong incentives for this thing. So I just want to point to 3 papers that if you want to read more about the dangers, and that's not really my talk today, but there you can read about that paper there. I still stand behind. It's 3 years old, 4 years old now, but it talks about this emerging engineering field. I responded with there was a bunch of response to that. It was a very nice, 10 people responding, and then I wrote something about economics. And this paper is here's all my colleagues that wrote this paper together. This is with social scientists. And so they're talking about what's wrong about autonomy. One of the problems that they point to about autonomy is that you have to have small teams creating these artifacts. Because if a big team of 100,000 humans create it, it's not really intelligent for all the intelligence came from humans. So Wikipedia or a search engine is not viewed as an AI because all the humans put all the knowledge into it. But they're smart. They're smart as anything else I know. But it's not working. So it has to be in small teams, and that's bad because that centralizes power. It creates AI in the hands of a small number of companies, and that's just kind of a bad dynamic. Okay, so if you go to machine learning people and you say, okay, this is a problem, you're not thinking about the overall system. They say, yeah, no, sure we are. For example, there's federated learning. That's an example. So federated learning is a decentralized paradigm where you have a server. It's trying to build a global model. So think Google, and there are many edge devices. So think cell phones. And so why is this paradigm interesting? Well, Google's trying to collect more data to train its models. That means more language data, more speech. Okay? So it says, well, we don't have all that data. We can go get it from cell phones. So why should people give data to Google? Well, it's not clear people want to give data to Google. Partly they just don't even know they're doing it. So Google says, we'll provide privacy, we'll compress the data, we'll make it all a good engineering system. But it's not being thought of the right way. Because people are involved, and they should be involved explicitly in this system. Right? So there's missing economics in this system, missing utilities of humans who create the data. All right. So in fact, the nodes in these things are often people. It's not just edge devices. And the data is not just things like what they're saying on their cell phone or where they're located or something. It's things they created. So people write novels on cell phones. They create songs on cell phones. They do all kinds of creative apps on cell phones. And that data is now viewed as public and going up to Google, who now owns it. That's just wrong. And so this is actually a broken system overall. So how do we fix this? Well, one thing you can do is complain and say government should regulate it all, and that's just not my style. My style is saying, what's the bigger problem? Okay, and the bigger problem to me is there's a missing notion of a market. It's just not there in this paradigm. So let's think about that missing notion. Okay, so first of all, I've worked on this in the real world. So there's a company called UnitedMasters.com And I'm the scientific advisor of this company. The CEO is Steven Stout, who's a brilliant, legendary producer in the hip hop and the music industry, very well known by lots of famous musicians. And he and I sort of shared the same perspective from, him from the music world and me from the academic world. That the goal of streaming data on musical data is to create a market. It's not to simply stream data. All right, so if you look at some actual data, so I know about the US data, huge amounts of music is being streamed every day, huge. And most of the songs being listened to today were written in the last 6 months, like 95% of them. And most of them were written by people you never heard of. Okay, so it's not the case there's a few great musicians that everyone listens to them. That's what everyone believes, but it's just not true. And most of the people you never heard of are like 20-year-olds. And they're really good at writing music that people really listen to, other 20-year-olds. And people walk around all day listening to music. So this is a worldwide phenomenon. All right, so that sounds great. Thank you. I'll take some black rock. Thank you. So that sounds great. It sounds like computer science has created this great platform that music can go around the world. That sounds wonderful. The problem is that those 20-year-olds create the music on their cell phone. It gets uploaded to Spotify, and then Spotify takes it and makes money from it. And that's broken. Right? The 20-year-old has no chance at a job, and they don't. After they're 25, they're no more music career. They have to do something else. All right. So United Masters says, okay, that's wrong. So what we're going to do is we're going to create, first of all, just simple data, analysis and data science. If you're a musician, and now there are 2.5 million musicians signed on. This is a working system, 2.5 million in the US. If you're one of those musicians, you go there and you have access to data. So at the end of the week, you see a map. So if it was in India, you see a map of all of India, and you'd see, that in Mumbai, 10,000 people listened to my songs last week. Okay? I know I'm popular. I don't know why. Someone liked it and told their friends. The venue owners in Mumbai can see that too, and I say, why don't I come give a show there? They say, yeah, the data tells us it's a good idea. You go give a show, you make, some thousands of euros or dollars. Okay, if you do that 3 or 4 times a year, you start to build up a salary. You have a portfolio. All right, so that was kind of the beginning of the system, but then it went even further. In the United States, there's these 2.5 million musicians who are making really good music, and Steve went to the National Basketball Association, NBA, and said, when you play music on your video clips, what music are you doing? And they said, well, Beyonce or Kanye or whatever. We pay the record companies a lot of money for that. And then there goes to the musicians. Okay. And Steve said, well, what about using United Masters? And they said, yeah. So they signed a contract. So the music now on the NBA website is from United Masters. And every time you listen to one of those pieces, the musician gets the money. Okay. So this is a working system, and there are now 2.5 musicians, many of whom are making enough money to have a salary. Okay? All right, so what's the AI behind this? Well, in some sense, that's the point of my talk. It's pretty simple. It's do data analysis, do a matching market, like in the microeconomics sense, and worry about the long tail behavior. Just make sure that 10 people are happy. Everybody's happy. And do the mechanism design and the economics together with the machine learning to make this work. And that latter part is not trivial, and it leads to a lot of academic research. Right? But I want to emphasize real world kind of thing.
It's not just a data curation platform.
No, that would be not an activist kind of thing.
Yeah.
It would allow some people to dominate and and so on and so forth. It wouldn't create an actual market. If you're a musician here, you know who's listening to your music. You can even contact them and say, would you like me to play your daughter's wedding? They can make an offer. You can have a bid. It creates a market. It connects things.
Non-trivial kind of welfare function.
Yeah, there's welfare functions and utilities and how to measure for revealed preference kind of thing. There's a lot of stuff that economics people say, yeah, that's us. We do that. Right? But economics people never thought about the data analysis and doing this ongoing. They just wrote down some preferences, made a market, done. They walked away. That's not the thing here. It's an online system. But I do want to emphasize it's not that complicated in some ways. It's not super AI came in and made something brand new that changed everybody's life. It's rather that we were thought about it in a new way and built a better system. Part of my message. Okay, so recommendations of systems in general are very, very important. But it's not just about the data curation and making the recommendations. And so let's just think, here's a typical recommendation system. Let's think about using this in real world problems that are not just recommending what book to buy or what, song to listen to or what movie. All of those things are things that you can copy as much as you want. So if you make recommendations of movies to people or books, and you happen, because your system is being used by a huge number of people, to recommend the same book to 100,000 people, I'm sure that happens every day in India. And people buy that book, and wow, that's great. You just copy the book. Or if it's a movie, even easier. Just copy the movie. All right, but what if you do that with goods in the real world that you can't copy, like restaurants? So if you recommend the same restaurant to many people, you created congestion. All right? And same thing with other things where there's scarcity. If you recommend the same street to every driver, the fastest route to the airport is that street. And you tell everybody that, you create congestion. Okay? All right, so I'm sure there's some experts on traffic here that I don't even know about, but this is wrong. And now, how do you fix this? And here's where I don't think the computer science training is very helpful. The Silicon Valley idea is that, well, it's just a load balancing problem. We can't send, 10,000 people to the same restaurant. So what do? We send, 50 to that restaurant and 50 to this restaurant and so on. Which 50 people? Well, we supposedly know a lot about you because we know your whole browsing history. We've learned about you, like in an advertising market. So we decide, we being like Mark Zuckerberg, decides who goes to what restaurant. I hope you can see how dumb that is. That's not going to work. That's not bringing out social value and social utility. People have preferences. They need to be learned about their preferences. They need to bid. They need to be part of a market, not just that some system tells them what they want. Okay, so there's a better way to think about this. And so now we turn to the academic part of the talk. Okay, so if we're going to think about this, we got to start to face some really interesting problems. My next slide is, these are the ones I think I'm going to mention explicitly in the talk. I'll give you some actual problems, some algorithms, and some theorems, and even a couple of deployments. And I'll do it kind of quickly because I have limited time, but I just want to give you a flavor of some of the bigger agenda here. And explicitly, I'm hoping that some of the young people in the audience will get interested in this. Many people are now working on these problems. To me, this is where the action is. It's not about deep neural nets anymore. That's, you can do gradient descent and tweak that all you want, but this is much more interesting. So the number one top bullet there is about relationships among optima, equilibria, and dynamics. In machine learning, we're very good at finding optima. If I was in high dimensions, it'll go find optima. That's great, right? But in these systems I'm talking about, there are no optima. Okay, there would be an optima if some supreme being looked down and told everyone what to do. But we'll never arrive at that optima. So we want equilibria, and we want good equilibria, and we want to design the equilibria. But the equilibria are never fixed. That's classical economics. Rather, the equilibria are always moving in conditions. So you want dynamics that follow the equilibrium. Okay, so that's fixed point theory, and it's stochastic fixed point theory in high dimensions. Something that von Neumann would have understood as a problem, but no one worked on for 50 years. But now it's coming back. Just like gradient descent, no one worked on it for 100 years, and it came back. And it drove deeper. Well, things point out that they're not coming back.
Quite complex equilibria rather than inefficient.
Well, there's no. The equilibria are not inefficient. Okay? No. There are different kinds of equilibria. There are Nash equilibria. They can be very inefficient. There are Stackelberg equilibria. They can be better. There are Rousean equilibria. They can be better. Now we're thinking about it like a design problem. I'm an engineer, and my goal is to design a good equilibrium and design the mechanism that arrives at that equilibrium. I just say, it's a bad equilibrium. It's inefficient. Okay? Yeah, it's interesting to have a reaction. It's kind of funny. I give algorithms talks or statistics box, and everyone says no problem. I bring in markets. People say, no, markets are terrible. They have problems. They're bad. Okay? True. Markets can have problems. Without markets, we wouldn't be here. They created all of the things we have, humans have. Right? So a metaphor I like to use, again, going back to engineering, is that 200 years ago, you could have said, as civil engineering was developing, people said, we're going to create this new field called civil engineering. It's about building buildings and bridges and structures. And we're going to use Newtonian mechanics and gravity and all that to build these things very nice. And someone will say, well, no, gravity, that's a terrible thing. Gravity kills lots of people. Okay? Because think about it, every day, how many people die because of gravity? Huge numbers, right? So you should not work with gravity. So you can now say, okay, fine, I'll build a version of civil engineering that uses no gravity. It'll use lots of pulleys and ropes, all kinds of things. There no gravity is allowed. You can do that, but obviously it wouldn't be enough. So you get my metaphor, that markets are powerful. They just naturally emerge. They're a force of nature. Some of them are good, some of them are bad. If we do the understanding of them, we can help design better ones and use that force but build around it.
Even the welfare theorems, state markets are like equilibrium are as you said, it depends on the equilibrium.
Well, yeah, so the welfare theorems are theories, and they're very, very strong, certain assumptions, certain things happen. Same thing happened to me in statistics and machine learning. There were some theorems that say, here's something that's statistically efficient. Kramer lower bound, blah, blah, blah. You can't beat that. Unbiased estimators. Turn out to be all correct, but not really right. 30 years later, we remove all those assumptions and we do the real stuff. Same thing is happening here. So all those things had a lot of assumptions about everything was known a priori, no hidden variables, no, all sorts of assumptions. Those are all wrong. So let's work harder to get rid of the assumptions and start to build a better version of it. Okay, it's not going to be the world, it's not going to be ideal, but it's going to be way better than anything we have right now. That's the hope for me. At least.
Multiple equilibria.
Yeah.
I think the best equilibrium except for the
we can't find the best equilibrium. Just like if you have multiple local minima, you cannot find the best local minima. That's a theorem and it's even true. But you can design systems, and that's what deep learning does, such that if you start in a reasonable place, most of the local equilibria are findable, and most of them are good. There's also all theory about that now. So if you'd given up and said, well, we can't find good global optima, that would have been a bad idea. Okay? It turns out it's just not the case. So yes, there are multiple equilibria. And so what you can do is things like, how do I get to an equilibrium and then move with that equilibrium? I don't just go off crazy. Or how do I initialize systems so it's near some reasonable goal? How do I make sure that the agents themselves drive away from bad at minimum? So I think I'll have a couple of
it's a dynamic mechanism design problem. So the equilibrium also could change.
Exactly. I'm totally agreeing with you. I'm just saying that's the problem that we have to face. We can't say, but it's too hard. We have to say we have to work on that. And we do. That's the rest of my talk. Is algorithms and machinery and theorems. Okay. Everything you can prove is impossible. Give you a general proof that everything is NP-hard and Sharp-P and TP pad complete and blah, blah, blah. And complexity theory is very useful, but it really gives us the wrong mindset. Okay, here I think is a better mindset, which is to recognize now let's move back to academics, that there are three kind of foundational disciplines of this emerging thing, computer science, statistics, and economics, and they've been brought together in pairwise kind of interactions. So computer science and statistics, that's what machine learning is. It's nothing different, it's really just that. Statistics meets economics, that's called econometrics, and that's really about measuring the economy, right? Now, machine learning is missing the third leg. There's very little economics in machine learning, very little incentives, equilibria, and so on. Okay? Similarly, econometrics is missing the computer science. There's very little mechanisms, algorithms in econometrics. Now, there is another field which blends economics and that's called algorithm game theory. It has its own conferences and people. It's like the design of new kinds of auctions and stuff that are more efficient than previous auctions and so on. But there's no statistics here. It doesn't look at data analysis and adjusting based on new preferences. It assumes everything's known a priori. That runs the algorithm. All right, so you can see there's an opportunity is to be in the middle here. I think that new emerging departments want to be in the middle, and a lot of the students want to be in the middle. And I say this partly because of my experience in industry. Like I do a day a week at Amazon, and any new problem that's being worked on, for example, the third-party sellers have this information, we don't have that information, the customers demand this. You get a team of 20 people, there's always people from all three of these disciplines, and operations research and control theory and a few neighboring disciplines. But if you just take one of those disciplines, your company will fail. You really need all three. Okay, so let's talk about an example of this. This is what I'm going to now give as many until I run out of time, examples of projects that start to get into some of these issues. So this is going to do, with my colleagues at Berkeley, something which is new, which is taking contract theory, which is part of the theory of incentives in economics, Nobel Prize given, but it has no statistics in it. So we're going to define a new problem called statistical contract theory and show you a use case. Okay, so the theory of incentives, just very briefly here, is a general theory of incentives and mechanisms. Okay? You know about auctions? That's one branch of the theory of incentives. It's based on equilibria. So theory of incentives and mechanisms are like inverse of a game theory. Game theory says, here's the game, what's the outcomes? Mechanism design goes the inverse. It says, here's the desired outcomes, what game will deliver those? All right, so if you look at Nash equilibria, that's auctions. Nash equilibrium, a bunch of players come to an auction, they all want to buy the same thing. They have different valuations, but they arrive at a Nash equilibrium, and we want in an auction to design a good Nash equilibrium. That's what second price auctions do. All Most problems in real life are not Nash equilibria, however. They're more like Stackelberg equilibria. And this is where there's asymmetries. Okay, so people have different information. And I would like, I'm a principal, and I'd like to get someone to do something, like a student. Right? And I need to pay them, okay, or incentivize them in some way. All right? How much do I pay them? Well, it depends on how much they already know and how good they are and how efficient they are. I don't know those things. And if I ask them to tell me that, they will give me the wrong answer because they will think, oh, if I tell them a different answer, then they will know how efficient I am. I'll make more things faster. I'll make more money. So they will lie. They're incentivized lying. People do. Okay, so the theory of incentives, called contract theory, is asymmetric Stackelberg equilibrium and finding good Stackelberg equilibrium. Now, you know about this because, you've seen this. It's happened in certain industries. Their airplanes famously use contract theory. This is where the Nobel Prize came from. So in the 80s, the airlines were about ready to all die. All the national airlines were dying. It's because these low-cost airlines came in, and they gave these really cutthroat fares. And the big airlines couldn't compete, right? But then they did a little bit of economic thinking, which is that, what if I don't use the same price for every seat in the airplane? Right? Well, how do you do that? So it's like in a movie theater, it's the same price for every seat, right? How would you give a different price for different seats? Well, you can't do price discrimination. I could not look at Chiru and say, oh, well, that's a professor. Obviously, he's willing to pay more money. I will make his fare be, $900. And he says, fine, I got a lot of money. And I look at a student and I say, oh, I see, you're a student, your fare is going to be $100. So what will happen is that Chiru will start to dress like a student. And he will pretend to be a student and he will get this nice cheap fare and he'll be very happy. Right? And everyone will do that. And the airline will no longer get their big fare. So you know what happened. And this was actually, it needed mathematics to support this. You couldn't just start doing this. It would fail. They did mathematics. And that's called contract theory. And so what it is that, you offer not just a fare, a price. It's a price and a service, and a price and a service. And there's a list of them. It's a contract. Right? And you give the same contract to everyone. And people look at that and they self-select which of those that I want. Right? For the airlines, it's kind of obvious and easy at some level. One of them says you get to have first in line and slightly bigger seat, and you get a little glass of red wine. And you pay $1,000 more for that. And the students here will not believe that, but there are people that are happy to do that. Okay? And they feel very good about themselves, standing in line with their little glass of wine and sitting there, very good about themselves. And the airline's very good because they suddenly got $1,000 for that seat. Now, everyone else pays much less. They don't get their wine. They're not first in line, but they're very happy too because they walk past that little section and say, you guys paid $1,000. I'm paying $100. I'm on the same airplane. So that's called social welfare. And you can quantify that. And now you can design a menu so you maximize social welfare. That becomes a problem you can solve. And the mathematics is actually interesting. It's not just optimization theory. It's a little bit different. Okay. All right. So this is kind of the problem. But now we're going to do this with data analysis. Because that setup and all those theorems were no data analysis. You just had someone think about it and draw down certain curves across certain places. All right, here's an example of a really interesting, important data analysis. Clinical trials. So these are numbers from the US. These are a bunch of diseases, and these are phase 1, phase 2, phase 3 clinical trials. You can see how many millions of dollars are spent every year for every drug, for every area of medicine in the United States. So what's happening here? Well, this is just that there's an agency called the Federal Drug Administration, FDA, and they're being statisticians. They're looking at a drug and they're testing it out on, say, 20,000 people and doing an A/B test. Yes or no, does it have an effect? And you all know this from the vaccines. The vaccines were done on 36,000 people, and the false positive rate was set to be very, very low, and the false negative rate was set to be low, too. They did a great job of designing and testing vaccines, as you all know. So we have some very good statisticians working in this place. Is statistics enough? The answer is no. Really, you should think about this as contract theory. There's a principle, that's the FDA. They want to get some job done, which is put drugs on market. Right? But they can't do it themselves. They rely on pharmaceutical companies who bring in the drug candidates. Because they have the engineers, they have the know-how. And so the FDA's job is to screen the results, the things from these. So it's not just they collect data and analyze it. There's an incentive structure. We have to reveal that incentive structure. Okay, so first of all, how should the FDA test? This is just the statistical part of it. And if you go to the FDA and you ask them, what are you doing? This is what they say. We're doing name and Pearson testing. If you're a statistician, you know it's an optimal testing paradigm. If the drug is a bad drug, meaning that the drug is actually not hurting people, that they test for that. It doesn't hurt people. They do animal models and so on. But if it is a bad drug, then they set a test statistic so that they approve the drug with a false positive rate of 0.05. It's actually 0.005, but these are just some rough numbers. And moreover, if the drug is actually a good drug, they set it up so the test will approve 80% of those. That's the power. These are typical numbers in industry. So is this a good protocol? Well, it's optimal from a statistical point of view. You can't beat it, okay? But it's not good, actually. So here in case one, you have a small profit to be made. So it costs you 20 million to run a trial. That's kind of typical. And if you were approved, you would make 200 million over the first year. That's a small drug, niche drug. All right, so if you're in that market, the CEO can do the following calculation, and the FDA can do the same calculation. It says, if the drug is actually not effective, I don't know if it is or not, but let's imagine counterfactually that it's not effective, then my expected profit is minus 10 million. I just put in those numbers. And so the CEO looks at that number and says, oh, listen, tells the scientists in the company, do not send a drug to the FDA unless you're very convinced it's a good drug. How do they know? Well, they did some internal testing a little bit. They have some rough idea. It's not good enough, but they have a rough idea. All right. So in this case, the FDA is only getting candidate drugs, which are mostly pretty good, and everybody's happy. If this were the case, it'd be fine. But here's really more the real case. It costs you 20 million to run a trial, and then if you're approved, you make 2 billion. That's more like ibuprofen, and ibuprofen is even larger than that. Okay, so this is for typical numbers. And so the CEO does the calculation. If the drug is actually not effective, my expected profit is 80 million. Why are you making money from a drug that's not effective? Well, there's a false positive rate, and you throw up a lot of drug candidates, and some of them go through the process as a false positive. In fact, many. All right, and they go on the market. They don't hurt anybody, but they don't help anybody. There's tons of drugs like that on the market. And then after a few years, there's somebody who develops a better one, and it gets displaced, and no harm done. A lot of money was lost. Right? And the problem is this really is much more close to what's happening in real life. Okay, so how do you fix this? Well, I hope you can see this is just, if you did contract theory here, you would be able to fix this. Okay, so we said, let's do that. We have a new theory, which we call statistical contract theory. And I won't give details, but let me just say this is what a contract looks like. You're an agent, and you look at the contract, and you say, either I opt in or I opt out. If I opt out, I just walk away, fine. If I opt in, I pay a reservation fee, like 20 million, and then I'm going to select a payout function, how long of a license I will have for my drug. And it'll be from a menu of payout functions that the mechanism designer designs, okay? Just like in regular contract theory. Those would be like, economy class and business class, fares and all that. All right, but here's what's new, is now you run a statistical trial that yields a random variable z from the true distribution, which no one knows, but nature knows it. And so when you run the clinical trial, you're sampling from this distribution. Okay, so you ran a clinical trial, z is the outcome. Okay? And in there's evidence whether the drug works or not, but it's just evidence. All right, so now the agent gets to receive a payoff depending on which option they selected based on the clinical trial. And then the principal, the FDA, gets a utility based on that amount they had to pay, because they have to pay this person receives it, they pay it. And also on the true state of nature, because after a few years, people will see the FDA is doing a bad job or a good job. Okay, so now we can do a theory of this, and we have, and we now know how to design contracts for the FDA. We're starting to work with the FDA, actually, on this problem. Let me just sort of skip 2 slides here, but just to say what's on there. There's a little bit of a theory here. So the first thing when you do when you take machine learning, you add in incentives, is you have to say what's incentive compatible. Okay, and so we did that here. So incentive compatible, a menu now is incentive compatible. It's not an action, the whole menu is incentive compatible if the expectation over the clinical trial under the null hypothesis of the amount you pay out minus reservation fee is negative. Otherwise, the FDA would just be losing money. So they wouldn't play, nor would the agents play. Okay, so that's incentive compatible. And we now have a theorem, which is right here, which is a contract is incentive aligned if and only if. So this is a characterization. All the payout functions are what are known as E-values. And E-values are something I don't have time to discuss, but there's the definition right there. They're somewhat like p-values in statistics, but they're better in some ways. They're more of a Bayesian p-value. They are a random variable whose expectation under the null hypothesis is less than or equal to 1. So if you know some mathematics, this is kind of like a non-negative super martingale. And these things combine in nice ways. They have nice statistical properties. That was already known. we've shown is that they're in one-to-one correspondence with optimal contracts in statistical contract theory. Okay. All right. So we've been using this to design new protocols for things like federated learning, where you have these people at the edge and you have the central server, and the central server now designs a contract that it gives to everybody at the edge, and they decide to opt in or opt out. And this does things like solves the free riding problem, which is known as a big problem here. If two neighboring edge devices are sitting next to each other, they realize they have the same data because they're close in space or something. They'll look at each other, and if this guy sends in the data, this guy will say, I don't have to. That's called free riding. And this framework allows you to quantify and to mitigate free riding. So this is kind of about that bit. Here is the paper that does this, and Praneeth, I don't know where he comes from, actually, in India. Praneeth Karimreddy. I don't know if he's from down here or from up north. But
I should be from some part of it.
Yeah, probably. But anyway, Praneeth is my colleague in a lot of this. He's an expert a world expert on federated learning, and he's joined my group and has become now a world expert on contract theory and application. So this is just starting. We have like 2 papers. For those of you interested, there's a whole lot to do here. This is just brand new topic.
Does this extend to something like this covers principles?
Yeah, it does. Exactly. E-values extend, it's just different E-values. That's right.
The if part was clear, but not the only if part.
What was clear?
The theorem there.
Yeah.
The if part was clear, but not the only
The if part was clear, not the only if. Yeah. The if part is totally clear. You're absolutely right. You can see that. The only if is the part that's non-trivial. That we're using some actual mechanism design techniques there. And I could get, it's kind of usual. It's not that hard. It's just a kind of math statement. It's proof by contradiction. But it's the kind of the core of the argument is exactly all that. In fact, there's you can also define a minimax value of the statistical gain. The best under worst case assumptions. And there it turns out the optimal contract is all E values, not a subset, but all E values. So it's really a nice connection. How much more do I have, Chief?
5 minutes.
Another 5 minutes. Okay. So in that case, let me just think about it. So I had 4 little vignettes. I've done 1 pretty slowly, and I can't do all 3. So I'm going to kind of select as I go here. Think about what's best for you guys. So strategic classification, I think I'll skip. This is kind of classification where, here, let me show a picture of it as you get a flavor of what it's like. This is where there's a central agent again who's collecting data from a bunch of strategic agents. They send in the data. The central guy makes a predictive model, and then people look at the model and they send in new data, and this loop continues. So these people have a desired outcome. They want to get a loan or get admitted to school. So they don't necessarily send in the true data. And so the system has got to recognize it. So again, a Stackelberg game, and we design a good Stackelberg mechanism here. So let me just sort of skip the rest of that. Show you there's all the way to kind of a setup of the problem. We do different time scales and different problem classes. And then there is a theorem, which is that under leader-follower Stackelberg equilibria, there's an equilibrium here, which is actually best for both the central decision maker and for the edge devices. That's actually a surprise. Usually equilibria are best for one versus the other. Trade-off. Here, there's a certain kind of equilibrium which is best for both. So we really learned something about new kinds of Stackelberg equilibria. It's not true for all Stackelberg equilibria, it's true for these Stackelberg equilibria. I'm going to skip this talk part of it too, and I'll do my last 5 minutes on the last part. So this is about bandits, which are making selections in matching markets. You all probably know what bandit algorithms are. They try to find the best arm of a set of options by doing statistics and exploitation. And there's algorithms that do this optimally. That's on the learning side. On the economic side, we talk about matching markets. And this says that there's buyers and there's sellers, and you want to find an optimal matching based on the known preferences on the two sides. In the bandit algorithm, you don't know the preferences a priori, which arm I prefer. You explore and you exploit. So if you merge that style of thinking with matching markets, you get this kind of new kind of competing bandit market. And this is kind of like a restaurant sort of thing. I go into Mumbai, I've never been there maybe. I need to try out some restaurants, but I also want to find the restaurant I like the most. But I can't go to any restaurant because there's constraints. So it's a matching market plus learning. So that's what this paper is about. And we have a theorem here. This is actually kind of an interesting theorem. This quantifies the regret, and it turns out we get an optimal logarithmic regret, but there is a constant term there that's new, and that's coming from the economics. That constant term is a bit small, you have lots of competition in the market. Okay? Lots of people want to go to the same restaurant. So it takes you longer to find the optimal restaurant for yourself. And if that thing is big, there's not much competition, you find the optimal thing much more quickly. So that's what our goal in all of this is. This kind of has an optimal learning rate, that's the log n there. It has some various constants, and then it has the economics. So learning with economics in one equation. That's what, to me, an engineer should do, is deliver these kind of nice little equations that have all the ingredients in them and have a trade-off. Okay, so the last few minutes, let me talk about this project, which doesn't have so much economics in it, but I think it's really a cool project and is kind of the basis of a lot of what we do. These are all some of my students at Berkeley who've been working with me on this. We call this prediction-powered inference. And the setting here is that you all know there's things like AlphaFold that can predict very, very well. And now the question is, can you do science with these predictions? Okay. All right. So, here comes a prediction. You want to try to make an inference. Now, there are hundreds of millions of predictions now for AlphaFold. The ground truth, though, is there's only hundreds of thousands of amino acid sequences where we know the true state, like we did crystallography. So there's a big mismatch here between these two things. Question is, does it really matter? Are these so good that they just dominate? All of science is done with these, and don't worry about those nearly as much. All right, so here's an example of this. This was an important paper in 2004. Someone was studying the relationship between intrinsic disorder of proteins and phosphorylation. Intrinsic disorder is where a protein doesn't fold. It's actually disordered under quantum fluctuations. And that's actually important for some proteins. They need to be more strand-like and less clumpy. Okay? And this person was kind of looking at that, this team. Phosphorylation sort of indicates whether the protein's doing something, roughly. So they said, okay, let's look at all the data. And here was all the data. They had 10,000 structures in the protein data bank. And they tried to compute a certain statistic and do a hypothesis test. And the answer was they couldn't make a decision. There was not enough data. All right, so now we come to 2022. Someone says, now we have not that much more new data. We have all these predictions. Okay, so why don't we just throw in the predictions into this statistical test? And so what's statistical test? Well, it's an odds ratio. So the probability of intrinsically disordered given phosphorylation, over the negative. So this number, if it's different from 1, means there's an effect. Otherwise, not. You want a confidence interval on that number. All right, so if you are using all those predictions, then you can get a really good confidence interval and really make lots of good statistical inferences. All right, so, and this is being done in tons of other problems, imaging, evolution, electricity access, and so on and so forth. All right, the problem is that AlphaFold, here's a prediction. This is the actual experimental structure. It makes some errors. So that's actually a disordered region. The question is, there might be just a tiny number of errors. Maybe it doesn't matter. Okay, but the way you solve that problem, or the way you think about it, is you're a statistician now. You say, well, let's take the quantity you care about, the odds ratio, and let's put a confidence interval on that. So if you do that with all of the huge number of predictions, here's the confidence interval. Really small. It's using all that data. The problem is that we did a Monte Carlo simulation to find out the truth, all right? And the truth is here. So it's a 2 point something. The confidence interval is not even close to overlapping the truth. This is really bad for a statistician. Right? So a statistician would say, well, don't do that. Just use the existing data, and we'll wait till there's enough to make good inferences. That's what science does. So here's the existing data being used, and it does cover the truth. There's a theorem that says it will. But problematically, it also covers 1, so you can't actually make a decision. This new procedure, which we developed, we call prediction-powered inference, is the best of both worlds. It gets small confidence intervals, but it also provably covers the truth, just like a good confidence interval should. All right, so let me just say, so here's kind of the setting. It's like semi-supervised learning. You have some labeled data, some unlabeled, but it's not supervised learning. You're not trying to improve the predictions. You're trying to use the predictions to make confidence intervals. And let me just sort of show you doing this for a range of problems real quick. This is for voting. Here's a ballot and some votes, and here's a corrupted ballot where some noise is included on the ballot. And so computer vision algorithms are used to take all the ballots and make predictions. And you can predict the outcome of the election by using computer vision. Sounds great. Problem is, if you do that, you get a confidence interval. It's really small because you have so much extra data, but it's not covering the truth. Okay. Here's predicting spiral galaxies with computer vision. You look at the sky, you might decide something's a spiral galaxy or not. You don't have enough humans to annotate it, so sure, let's use computer vision. Problem is, you make an inference which is far from the truth. Here's another one in biology. Here's my favorite one. This is something from the California census. You're just trying to decide, you look at the regression coefficient of income when predicting whether a person has private health insurance. So it's the sociological, study, and you're trying to make a prediction of something that's relevant to healthcare. And here's the problem. Here's the confidence interval using all the predictions. Here's the truth. You're really sure, and you turn this, you get back to the government regulatory agency. Look, I did it. I'm really sure. You're completely wrong. So this, I think, is a serious problem. And so our new procedure fixes this. Let's skip this one here. I'm going to show you on one slide, and I'm going to finish at this point. So there's a paper that you can look at. Roughly speaking, this is for the more technical people in the audience. What it's doing is it's recognizing there's a bias between the prediction and the truth. That bias is unknown, but it's a parameter in the population, and you can put a confidence interval on the bias. It's looking at all the possible biases given this labeled data set. And it's taking the prediction and it's correcting that with all of the possible biases in my confidence interval. That gives me a new interval here in which the truth is guaranteed to lie. Okay? So we have a theorem that says the truth lies in this new corrected interval with the asserted probability. And this is kind of working out the mathematics for the case of gradient-based algorithms like neural nets. Okay, so I'm finished. Let me just return to that last slide and leave it up for questions. I didn't give that much detail on that project, but I hope that you sort of see there's something really interesting here. It's brand new. We did this work like a month ago. And it's still working on it. All right, thank you.
Any questions?
Yes.
So in the statistical contracts problem, we managed to give conditions on good contract structure, right?
Yeah.
But we still have the problem of estimating the distribution.
No, we don't have, I mean, we have, it's a statistical problem we know how to solve. We don't have to make parametric assumptions. We can use non-parametric testing procedures for which we're experts. That's absolutely right. So there's a whole other talk I think I'm going to give later in the week here on non-parametric, conformal prediction and non-parametric testing. That's something we've worked on for all these years, but we never put it together with the statistics. You're absolutely right. You have to do the statistics right. Otherwise, none of this makes any sense. So that's not exactly right. Yeah.
Fantastic talk. If you bring in economics into play, the performance of the algorithms without economics is going to degrade.
Yes.
Right?
Yes.
So is there some general idea of by how much this performance will degrade?
Fantastic question. So that's a research agenda for the next 30 years, really. That's what we're trying to do. And let me give you an example. So he's asking something that's really important, is that if you're a machine learning person, you might not like this talk. You say, well, the predictions are really great, but now you're doing something else to make better predictions. And those things are going to degrade the performance of the algorithm. I'm going to say, well, that's what we want. But how much? All right. So we did this for the area of privacy, just to give you another example. If you take a bunch of data and you privatize the data, the way you do that is you add noise. It's differential privacy. Now you take the privatized data, you put it into a statistical model, she'll do less well. You'll have less good prediction. The risk will go up. So the question is, can you get a curve relating how much privacy you guaranteed versus how much the risk went down? Okay? And we did that. Right? And so why do we want to do that? Well, privacy guarantees are not 1-0. It's not either you're private or you're not, okay? Like cryptography. If you ask for my medical data, my genome, for example, it's very private. I probably don't want to just have it out on the internet. But if you ask for my medical data, what I'm going to do is say, well, who are you and what are you using the data for? So that's about my risk function. And you'll say, well, I'm a doctor and I'm going to use it to analyze the disease that runs in your family. I'll say, fine, here's my genome. I'll give it all of it. Or if there's some other thing you're trying to do, helping the state gather statistics about certain things, I'll say, well, that's fine, but I'm going to only give you part of my data. If I add noise, part of it. If I have a knob I'm turning there, it gives me control over the amount of privacy I want, depending on my risk function, depending on the problem. Okay? Now, as I turn that knob, it's just like, when humans learned how to understand rupees or dollars or euros, they had to understand what it meant to have a certain amount of it. And they did after a little experience, right? And there was a market created for money. And here, so if I understand, if I set the knob right there, that gives me a certain privacy risk, right? But then I can now calibrate that against how much social loss there was in making a statistical inference. Did I understand the disease or not? So again, we did that. We worked out the kind of minimax theory needed for that in the privacy domain. But that's absolutely the kind of thing that's kind of driving a lot of the thinking here. Just quantify everything and make sure that you get your hands on every piece and then put them all together into a trade-off function. Because it won't be, you'll always do worse by, well, that's not true. No, I'll say something like that. But I mean, we see some win-wins where if you do this, you even get better on something, but often you will do worse. The question is how much.
So here again, I think different levels may lead to different degradation.
That's right. No, that's exactly right. So again, that's the kind of the agenda going forward. So we know we know the design of the optimal contract, just like Neyman, 100 years ago, knew the design of the optimal tests. But then it took 100 years to sort of find different kinds of tests for different situations. Are they computationally burdensome? Are they robust? Do they yield privacy trade-offs that are good? And that's what I want to work on too, is what you guys use for certain kinds of situations. It's a new vocabulary. How do we use that as a design tool and get actual trade-offs? So you're absolutely right. There are certain e-values which are very good at certain power parts, but they're not so good at this. They're not robust. New vocabulary.
No more questions. So, in the first question.
So in the first project you presented, so we introduced mechanism design, and
Yes,
as far as
I couldn't hear.
am I audible now?
No, you're just a little louder. Just talk without that.
Am I audible now?
That's better, yeah.
So in the first project you presented, when we introduced mechanism design,
Yeah.
does it make it easier to achieve things like fairness, which in neural nets seem to be an issue?
Yeah, so I'm glad you asked about fairness. Easier to achieve fairness is a little too vague, but yes, fairness is exactly the kind of thing I'm talking about here. Fairness is an economic concept. Okay, you can try to make a definition about certain conditional probabilities being the same in different demographics, but that's way too narrow. Okay, and then making sure a net neural net does that, probably it's not going to really do what you want. Fairness is a social construct. Okay, fairness is like, for example, if you're a seller of socks, right? And you need to advertise, make certain socks, wear it. So you advertise and you say, well, I have to make it fair. I have to make sure that everybody sees the same advertising. Well, I don't want to see, advertisement for yellow socks. I don't like yellow socks. Okay, if you don't want to see black socks or whatever, the person should be taking into account our utilities. That's only fair. It's fair to take into account what people really want, but you have to fairly assess what they want, not just assume it or not do the wrong thing. So fairness is all about measuring and knowing about utilities and trying to ensure that you respect utilities as you roll out a system. Okay, and so utilities, for example, the classical fairness is that someone got something and I didn't. Right? Well, my utility is terrible in that situation. Right? So if your system is supposed to make sure that all utilities are respected, it didn't. It's unfair. And again, just like privacy, it's not 0-1. You might tolerate a little bit of unfairness because there's other values associated with it. In fact, it's unfair that some people get to sit in the front of the airplane. This is just they have more money. But kind of we learn, we grow up, we become mature people and realize, oh, that is good. That makes more airlines possible. It makes more transportation possible. It's actually a good thing to have certain limited kinds of unfairness. So yes, unfairness can be thrown away around too much now. It's just a very vague term, but it's an economic concept.
It's the that similarity to the token distribution.
Thank you.
So for distinguished guests, we do some special thing for you. For distinguished guests.
You do. Oh, a shawl. Oh, nice. Yes. Thank you. Beautiful. What do you want to do? You're supposed to face this way?
Yes.
All right. You all just.
Yes.